started from the current slide. Okay. All right, I'm going to also scoot Morgan over, and she's always in the way, you know. No, I have a bar over here to the side, and it just, whoa, got rid of everybody except Morgan, so fine. Okay, so now, any other issues that you want to bring up before we start actually the class? Any questions on calculus, what we've done so far, anything? If not, I have just a couple of announcements here. First, I meant to say this on Monday and I kind of forgot, and sorry we're late getting started. This class has probably been my best class as far as getting research papers in. But that said, I only have 5 out of 20, okay? So that's my best class, okay? Please, folks, don't forget your research papers. Please get those in as soon as you can. Actually, technically, Monday is the last day I should be receiving research papers. Now, I'll take them after that. We do have class on Wednesday, but I'd rather not have all the research papers are graded at the same time I'm grading everything else. So if you could get them in Monday, that would be fantastic. Okay? Now, while I'm talking about that, the first test. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 20. That means 7 people haven't turned in the first test. Okay? Please get those in, if possible, by Monday. Okay, this is going to be a full weekend, isn't it? And then I think at the end of class today, I'll be giving you the second test, the Chapter 7 test. Okay? Now, I'm going to try to make it as straightforward as possible, but there you're going to have another test that you have, so please try to get that done. And then if we can finish Chapter 7 today, we'll get started on Chapter 8, which is Techniques of Integration, which to me is the most important chapter, and yet we haven't even gotten there yet. So we're going to get on that, and that's going to be Monday and Wednesday of next week. So at the end of Wednesday's class, I'll be giving you a very short final exam. Very short. So please get these other things into me before Wednesday, because Wednesday will be the last test, and that will be on whatever we get to cover in Chapter 8. Okay. Now, here's another fly in the ointment here. Hopefully it won't be an issue. But if you remember back probably a month, 5, 6 weeks ago, I had to make a trip to Georgia. My wife and I had to go to Georgia to take care of some business there. Well, we've got to go back, okay? So that means that we're leaving early Friday morning. I mean very early Friday morning, because my wife's being a infectious disease epidemiologist. We are going to have to make at least one stop for gas on the way, and so she wants to, when we do stop, by the way, we take our breakfast, we do everything, so we don't have to stop any more than that one time, but we do have to stop that one time for a break. She wants to be there as early in the morning as we can be when we need gas. So fewer people will have been in the store, fewer people will be around, fewer people will have touched the gas tank, yeah, just as all those reasons, okay? And then we'll be coming back early Monday morning. Now, I did this before. We got back in plenty of time. I think we were back here by 10:30, so I had time for to be ready for the class at 11:30. However, you can never tell. We have to go, through Atlanta on the interstate, and you can never tell what's going to be happening then. So if I'm not here right at 11:30 on Monday morning, don't go away. I will get here. I promise I will get here. And hopefully I'll be here close to on time. Okay? In fact, I hope to be here before the class ever starts. But who knows? Things like today could happen, and nothing opens up the way it's supposed to. And the strange thing is, I'd been on the computer all morning, everything had been fine, and then this after or late morning, it just wouldn't open a thing. So anyway, that's enough of my sad story. Any comments, questions, concerns before we get going? Now, let me go back to that final exam. I have to have it in sometime over the weekend. So I'll give it to you Wednesday after class. You have Thursday, well, you have Wednesday afternoon, Thursday, Friday, Saturday, and Sunday. Please get it to me before Sunday evening because I need to get them graded, and I think our grades are due in by noon on Monday. So I cannot be receiving final exams late, okay? I have to have them sometime Sunday afternoon or no later than Sunday evening. But I don't want them all coming in Sunday evening because I can't possibly get everything graded, all the grades posted and everything else in a few hours on Monday morning. So please, now that's not this coming Monday, it's the following Monday. All right, any response, feedback, question, anything? All right, if not, last time we got as far in 7.6, Chapter 7, Applications of Integration. 7.6 is moments, centers of mass, and centroids. And so far we've done moments and we're on center of mass. So we're about halfway through this section. Here's example 3. Find the center of mass of a system of point masses. Okay? M1 is at 3, -2. That's right here. M1 has a mass of 6. Wait, I said it wrong. 3, -2. It's right here. A fairly large mass down here at 3, -2. M2 is a reasonable mass, magnitude 3, and it's here at the origin. M3, mass 2, fairly small mass, it's over here at -5, 3. -5, 3. Okay? And then finally M4, the biggest mass, mass unit 9, and it's over here at 4, 2. Okay? We want to find the center of mass of that system. Now, if you remember what the center of mass is, it has an X component and a Y component. Okay. Now, the X component, and they do it by means of moments. Okay. So oh, wait, here's Joy coming in. Let me get her here so we can pick up and go from there. Joy is here. Okay. Now, the center of mass, as I was, oh, by the way, Joy, if you can hear now, we're in Chapter 7, Application of Integration, Section 7.6, Moments, Centers of Mass, and Centroids. We've done moments, still using them. We're now doing centers of mass, example 3, and that's what's on the screen right now. Okay? Now, it says find the center of mass. The center of mass has 2 components, an X component and a Y component. Now, the X component is the measure that the mass is from the y-axis. That gives you the center of mass for the X. So, for instance, to get your M sub X, you would take the 6 here, that's the mass, and multiply it by 3 units from the y-axis. Whoa, 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 here's Kira coming in. So let me get her here. Okay. Wait a minute. Okay. Kira is here. Okay, top part of the alphabet is really strong. The bottom part, poor old Joy and Aaliyah are holding it down all by themselves. So I hope some more get here. Okay, Kira, if you're here and can hear now, we're in Chapter 7, Applications of Integration, Section 7.6, Moments, Center of Mass, and Centroids. We're on the center of mass part, which of course is using the moments part. So, I was just saying the x component of the center of mass is basically your moment from the y-axis of each of these masses. Okay, so that would be a moment is a mass times a displacement, so it'd be 6 times 3, because that's the moment with respect to the y-axis, but it gives you the center of mass in x because you're dealing with the x here. Okay, so I think I will go, if y'all got a good picture of what's going on here, go to the whiteboard to do the calculations, because it's so much easier to do them from there, because if it'll come up, there it is. Now I still have to move this taskbar because it gets in the way of my writing. I don't think you can see it at all. And I also move the whiteboard to give me maximum white space. Okay. That's about as good as I can do. Okay. Now let me get my pen, my stylus on the Wacom, and let's do it. So I'll use the same nomenclature as the book does. I'll list everything the way they did, and they start with the masses. So I'm going to do the masses at the top. Okay, and mass 1 is 6, and its location is at 3, -2. I'm going to have to write all this down because, okay, it's at 3, -2. Okay, second mass is 3, and it's at location 0, 0, I believe. Yeah. I'm putting the locations in here too. The third mass is 2, and it's at location -5, 3. And the fourth mass is the big one, that's 9, and it's at position 4, 2. Now y'all check me and make sure I've written everything right. I'm having to go back and forth. Alright, now they call it the moment with respect to y, which is exactly what it is, and that's what gives you your x component of your center of mass. That seems a little backwards, but it kind of makes sense because it's the moment with respect to the y-axis is your mass times how far you are from the y-axis. Well, that would be where are you on the x-axis. Okay, so that would be how far. So your moment with respect to y, then for this one, if I can get the pen to come down, moment, remember, is a mass times a distance. That's 6 times 3. How far you are from the y-axis, 3 units to the right, plus 3 times 0, I think I can do that one, okay, plus 2 times -5, yuck, sorry about that, you probably can't see it, but it's a button on my Wacom that my hand hits sometimes. 2 times the -5, keep the signs, and plus 9 times 4. Okay, now let's see if we can do that kind of in our heads. 18 plus 0, I got that one, minus 10, that would be 8, plus 36, I think that's 44, isn't it? So the moment with respect to the y-axis is 44. Okay, now while we're doing that, let's go on and do the moment with respect to, I'm sorry, I'm saying x-axis as I talk and writing down y. Okay, well, it erased it for me. Maybe I need to use that. Okay, now it erased the previous thing I did. So let me write them back in here. M sub x. That's the moment with respect to the x-axis, but that's the mass times the y values. So this will be 6 times a -2 plus a 3 times 0, that's the one I can handle, plus 2 times a 3, plus 9 times 2. Let's see if we can figure what that one is. Negative 12 plus 6 would be a negative 6, plus 18 would be a positive 12, I think. Y'all do the math and make sure I'm doing it right. All right, and the one other thing we need, of course, is the sum of the masses. And the sum of the masses is just 6 plus 3 plus 2 plus 9, and that is 9 and 9 is 18 and 2 is 20. Okay, so what's your m sub x, the x component of your center of mass? That would be your, my knee gets stiff, sorry about that. That's why I'm grunting and groaning here. That would be your moment with respect to the y-axis. That's how your product of your masses times the x displacement. That would be 44 over 20, which looks like to me to be 11 over 5, which would be 2.2. Okay, let's do the m sub y, the center of mass coordinate on the y-axis, and that would be 12 over 20, which would be 3 over 5, which would be 0.6. Okay, so that's where I place the center of mass. And guess what? They left it as 11/5 and 3/5. Okay, sorry, I thought they were going to go to decimals. Okay, let's go back and see. So do you see how to do this? That's how you find your center of mass. The book does it, strings it out like this. Not a bad way to do it. Okay. The subscripts to me are a little bit, oh, whoa, I guess I have messed them up. I use the same subscript for 2 of them. Let me go up here to my eraser if I can get the pen to go there. Come on. Okay. Okay. I messed up the thing. This is called X bar and Y bar. I was using center of mass. So X bar and Y bar. Sorry. I was going to say I've got 2 m's of X's. So the X bar, which would be the moment with respect to the y-axis, because that's the masses times the x displacements. So I don't like to call it moment with respect to y because I think it has something to do with y, and it does a little something, but it's an x quantity, m times the x coordinate. You add those together and then divide by the m, and that gets you your x bar. Do the m times the y coordinates, add those together, divide it by the mass, and you wind up with the y bar. That's the way I think of doing it, but I bet you engineers will be talking about moments out of your ears, so that's why I go on and say moments, because that's typically what y'all focus on. Okay, and so we have 11. The center of mass will then be 11/5, 3/5. That's your center of mass for this system. So let's go back and see how the book did it. I think it's almost identical. 7.6 and current slide. And let's see. Oops, wait. Here comes Kyle. Okay, good deal. Kyle is here. Okay. Oh, I said here he is, but I forgot to let him in. Oh, is he thinking I've got a Freudian on him? Okay, never mind. Okay, so here's what we've got. Now, Cal, if you're in so you can hear us now, we're in Chapter 7, Applications of Integration, 7.6, Moments, Center of Mass, and Centroids. We have already done the moments, so we're still using them. and we're in the middle of doing centers of mass, and we've just done example 3, and we're going to see how the book compared. We found the center of mass, and I'm going to see if I can do it, 11 fifths, that's 2 1/5 about here, and then 3/5 about here. So this is where I would say the center. Ooh, it moved on me. Well, it's moving all over the place. It's not drawing. Let me try it this way. Something about like this. That is where we would place our center of mass. Does that make sense? Well, yeah. These two big masses have pulled it over near them, not quite halfway in between them, closer to the biggest one. That makes sense. This one had some effect pulling it back this way. This one, even though it didn't have much mass, is so far away that did pull it back a ways. So both of these are pulling this way, but they're small masses but large distances. These are big masses but short distances from it. That looks pretty reasonable. Okay, well, let's see how they did it. Well, they first put their 4 masses there and found out that's equal to 20. I did that at the end. They did it at the beginning. Then they did the moments, and I gotta wait until, okay, this goes away. There we have it. 6 times 3, that's 6 mass here times displacement x here, mass here, displacement here, mass here, displacement there, mass here, displacement there. That's how they came up with these numbers. And as soon as that moves out of the way, that would be 18 minus 10 would be 8 plus 36 would be 44. And as soon as that box will fade out, you'll see that's what they got. 44 is the moment about the y-axis. From the y-axis, that's measured in masses times x displacements. Okay? The m sub x is similarly same mass, but now we do it times the y values. 6 times -2 plus 3 times 0 plus 2 times 3 plus 9 times 2. That would be -12 plus 0 plus 6 would be -6 plus 18 would be a positive 12. Now, I don't know if you can see that or not, but now it's fading out. You should be able to see it. So there's your m sub x, which we use to get the y component of the center of mass. To me, the sub x's and y's are mostly confusing, but just realize that's what they are. So the x bar is my over the total mass, the moment with respect to the y-axis, which you got by mass times x displacement plus mass times x. Okay, that, and then divide by mass. It's kind of like you're dividing out the mass and you get the average x. That's not really what you're doing, but it's similar to that. You get 11 fifths. 44 over 20 is 11 fifths. The y bar, this was the y displacement, mass times the y displacement plus mass times the y displacement plus mass times y displacement plus mass times the y displacement. Then divide out the masses, divide by m. That was our 12 divided by 20 is 3 fifths. And the center of mass is then 11 fifths, 3 fifths, and they don't show it on the graph. Okay? Wish they did. I sort of put a mark there. Any questions on that? Now, the next topic here almost sounds daunting. The center of mass on a planar lamina. What in the world is a planar lamina? Well, that's what they're going to tell us. A thin, flat plate of material of constant density. That's what we mean by a planar lamina. Okay? Now, density, by the way, is a measure of mass per unit volume. Could be grams per cubic centimeter, kilograms per cubic meter, pounds per cubic foot, pounds per cubic inch, ounces per cubic inch. Lots of ways you can measure it. For planar laminas, however, the density is considered to be a measure of the mass per unit area because this is a plane. It's very, very thin. So you don't have to worry about that dimension. It's a mass per unit area, basically, when you're dealing with a planar lamina. The density is denoted by rho. You probably can't see it now, but as soon as this fades out, it'll be there. Rho is the Greek letter that corresponds to our R. I don't know how they get density out of that, but it looks like a P, but it relates to our R, the lowercase Greek letter rho. That's how we refer to density. Okay? Now, consider an irregularly shaped planar lamina. And by the way, the ones they showed up here were very regular shape, a circular shape, a square shape. Well, guess what? If it's a uniform density, thin sheet, the center of mass is smack dab in the center of that circle, or where the two diagonals cross in that either rectangle or square. That's where it's going to be, where you would expect it to be. Okay? But what if we have an irregularly shaped planar lamina? Again, uniform density, that means it's a planar lamina, bounded by the graphs of y is equal to f of x on top and g of x on the bottom. Okay? And also bounded by x equal a on the left side, x equal b on the right side. Okay? Very irregular shaped object there. What is the mass of that region? Well, that would be the density times the area. But we know how to do the area. Remember, the difference, think of this as your representative rectangle. The length of this rectangle is f minus g, and the width of it is dx, delta x, so to speak. Well, that's how you get your mass. It's the density times the area, and the area is the integral from a to b, f minus g dx. Okay, and you can shorten that. Let's just say rho times the area. Area we calculated before. Okay, so that's gotten you the mass. Now, how do we go about trying to determine the moments of this? That would be the next issue. To find the center of mass of that lamina, partition the interval from a to b into n subintervals with delta x. Boy, this sounds new, doesn't it? No, we've been doing this ever since we started doing integrals. Okay? Let x sub I be the center of the, this time we're going to let it be the center. Before we were saying at some point on there, the center of the ith subinterval. You can approximate the portion of the lamina lying on that ith subinterval by rectangle whose height is f of x sub I minus g of x sub I, just like we did before. Okay? That's the height. The density is fixed, because that's what we mean by planar lamina, constant density, rho. So the mass of that ith element there is the density of that, which is rho, times the area, which is f of x sub I minus g of x sub I. That's the height, and then the width is delta x. Okay, I'll let the window get out of the way. Yeah, there it goes. So there is your mass of your ith interval. Okay, a good approximation of it anyway. Okay, now, considering that mass to be located at the center of the rectangle, x sub I, y sub I, the directed, now we're going to assume that it's at that point. X sub I is the center of that, y sub I is the average. Okay, so the directed distance from the x-axis to x sub I, y sub I, that from the x-axis now, that is exactly the average between these two. F of x sub I plus g of x sub I, add the two together, divide by 2. That gives you your y sub I. Of course, the x sub I is x sub I. Okay, that's where you are. Okay, so the moment m sub I about the x-axis would be its mass, which we just calculated before, rho times the difference in the heights, that's the length times delta x, multiply by the the density, the different distance it is from the x-axis. That's your y sub I. which is f of x of I plus g of x of I divided by 2. I'll let the box get out of the way and you can see that. Here's the mass, rho times the length times the width, and here's your distance from the x-axis, your y sub I. Okay. Now, interestingly enough, you have this difference times the sum of the same two values. Well, that comes up to be f sub I squared minus g sub I squared. Sometimes the difference of the same two quantities, those are called conjugates of each other, gives you the difference of their squares. Okay? And they don't do a thing with it. Okay, sorry about that. I thought they were going to say it, but they don't. So here's the blurb, bottom of page 498, that summarizes what we've done so far. Let f and g be continuous functions such that f of x is always greater than or equal to g of x on the interval a to b in question. Consider the planar lamina to be of uniform density, rho, bounded by the graphs of y is equal f of x, y is equal g of x, x equal a, x equal b. So the moments now about the x and the y-axis, the moment is the mass, which of course the mass is the density times the area. The area is the height times the width. This part is your area. And then the moment is the distance that is from the x-axis, and that would be the average between f and g at that point, f plus g divided by 2. Now the moment with about the y-axis is even easier. Okay, this is your density times your height of that rectangle times the width of the rectangle. That gives you the area of the rectangle, and then multiply that by how far you are from the y-axis, and that's x. Okay, so this one's a lot simpler than that one. The center of mass, x sub bar, y sub r, is then x sub r is m sub y over m, total mass, and y bar is m sub x, this integral, over total mass, where total mass is your density times your integral from f of x minus g of x dx. That's just the density times the area. Okay, because we're considering a thin lamina have negligible thickness. Okay, I'm trying to let the window move out of the way. So that's the mass of the lamina, and that's what you put on your denominators here and here. Okay, I think we're ready for example 4, top of page 499. And by the way, for those of you who don't have this text, you're using your homeschool's text. If any of you are doing that, you can go to larsoncalculus.com for an interactive version of this example right here. Find the center of mass of the lamina of uniform density rho bounded by the graph of f of x is equal to 4 minus x squared and the x-axis, which is y is equal to 0. So we need to find out what the bounds are here. So since the y is equal to 0, we set this thing equals 0. So that's how we're going to start. Let me go to the whiteboard and we will do that. Any questions before I do? Let me clear the whiteboard of all its drawings. And first thing we do is set the f of x, 4 minus x squared, is equal to 0. Going to find the 2 points of intersection there. Well, we know how to factor this. This is 2 plus x times 2 minus x equals 0. So we know right now where this is going to be. X equal -2 and x equal positive 2. Now I'm skipping steps. I hope you realize that. I hope this is such old hat to you. You know how to do it. So that's our limit. This is our A. That's our B. We're going from negative 2 to positive 2. Okay? Now, I'm going to cheat a little here, if that's okay with you. If you picture this, this is a parabola. You can tell by those, the symmetry of this. Okay? That's a parabola. It's opening downward. The maximum value of that, which is your vertex, is going to be at x equal, y is equal to 4. When x equals 0, y is equal to 4, you'll never get any larger than that. Every other y is going to be less than that. So that's your maximum. And that's going to be where x equals 0. So 0, 4 is your vertex. Minus 2, 0, and plus 2, 0, those are the endpoints here. Guess what? Everything is symmetric about the y-axis. Remember, the lamina is a uniform density. So guess what? I can tell you where x bar is right now. 0. Because everything's symmetric about that. So your x bar is 0. They're going to go, well, no, they aren't. Because the center of mass lies on the axis of symmetry, you know x bar is equal to 0. So we've already got half of the problem done. Let me just write that down. X bar, the x component of the center of mass, is equal to 0. You can tell, if you don't like my verbal description of it, I'll let you see what this looks like. I don't have my picture up here anymore, so I can't see. I don't know why it disappeared here. Let me see if doing something here is going to make it. Okay, I can't get it to show up again. Can y'all tell me when I've got the figure adequately in front of the camera? Yes or no? Right, left, up, or down? Or can you even tell? Pulling back so you can see the whole page. Anybody? Can anyone hear me? Okay. I need to do what? Slightly downward. Do what? Oh, too close. How's that? All I want you to see is how it looks and why the x bar, the center of mass of x, has to be on the y-axis. You see that? Okay, I'm tired of holding the book. Okay, I hope you saw it. If you got your books, look in the book. Okay. Now, so what we have to do to get y bar, you need to do, yeah, I'm going to have to draw the picture here, am I not? Okay. Let me, and I don't draw good. Okay. I'm going to try to draw a vertical line. That's fairly close, but not quite. Hey, it's closer than I thought it would be. Okay, I'm going to try to draw a horizontal line. I can draw it down here if I want to. Okay, not quite horizontal, but we'll live with it. Okay, now I'm going to tick off some points here, so let me go back and get my thing. So this will be 1, 2, 1, 2, 1, 2, 3, 4. So here's my parabola, or at least my terrible rendition of a parabola. Something like that. And let's just take a, we know the x bar has got to be on the y-axis. Okay, so let's do a little rectangle here. And what we're looking for is the center of mass with respect to y. And now this is doing stupid things. Okay, all right, so center of mass here. Somewhere in there is the center of mass of that one. Okay, yeah. All right, now do you remember how we determined the center of mass of that one? Okay, well, first let's do the mass of the whole thing. That's the easy part. So let's do the mass. Come on, where's the pen? There it is. Okay, the mass of the whole thing is the density, which is a uniform density. That's why it's a lamina. And then you're doing the integral. And I'm going to cheat again here. I'm going to double this. I'm just going to integrate from 0 to 2. Makes the integration a lot easier, and double that because it's a uniform lamina. They're supposed to be symmetric. It's not in my drawing. 2 times from 0 to 2. And then what is the rectangle? Since I'm doing over here, let me draw a rectangle here. There, it did it again. Okay. This is terrible rectangles here. What's the area? Now we're just doing the area. Okay. The height of that rectangle is this, 4 minus x squared. Okay. So that's the height of the rectangle, 4 minus x squared. And what's the width of the rectangle? dx. And do that from there. So this is pretty easy to do. 2 rho. And then what's the antiderivative of 4? Hopefully someone was yelling out 4x. I just couldn't hear them. Minus antiderivative of x squared. Increase your exponent by 1 and divide by that new exponent. Okay? Evaluate this from 0 to 2. Okay? So this will be 2 rho times 8 minus 8/3. Well, 8 is 24/3 minus 8/3 is 16/3. So this will be 32 rho over 3. I did that sort of fast, but hopefully all of you followed, right? There's the mass, 32 rho over 3. All right. Now, let's back up and do the moments. We got the mass. Let's do the moment. And remember, the integral for the moment looks a lot like this one. This is the moment with respect to the x-axis because it's going to give us the y bar. And this will be, don't think we can do the 2 rho here thing. But yeah, it seems like we should be able to. I don't know if the book does it or not. Nope, they do minus 2 to 2. I think we probably could, but let's do it the way they do. All right, so it's just going to be rho on the outside. Okay, the integral now from -2 to 2. And I'm pretty sure we can. Let's do it twice. If it doesn't come out right, I'll tell you, I'll just go back and do this and it'll be right. Okay. Twice, 0 to 2. It's got to work. Okay. All right. Now, your part of this is just what we have here. Okay. The other part is your y value, which is exactly halfway of that. So this is the f of x, the 4 minus x squared divided by 2. That gets you your displacement from the x-axis, and then the rest of it is your area, okay, that you use, multiply the density, and you get your mass. So it's the same as this, except you also have this term in there. It's a f of x divided by 2. Well, guess what? We'll take that divided by 2 and cancel out that 2. Sorry. Okay, it'll go away. Well, you probably can't see it anyway. Okay, so that will be 4 minus x squared. We had divided by 2, it canceled that out. times 4 minus x squared dx. Okay. Now, you got a couple ways you could do this. You could call that 4 minus x squared squared. That's sort of a pain in the neck. So let's just go on and multiply it. So this will be rho times the integral from 0 to 2 of squaring this thing would be 16 minus 8, twice the product of the two, x squared, plus x to the fourth dx. Okay. First, 4 times 4 is 16. Twice the product of the two, 4x minus 4x squared minus 4x squared is minus 8x squared plus x to the fourth. Now let's integrate that. Okay, and what you have is rho times 16x minus 8x cubed over 3 plus x to the fifth over 5, evaluated from 0 to 2. All right. I think I'll come up here and write the answer. I know it doesn't make sense logically, but it just gives me more room to write. That moment, m sub x, is rho times 32, plugging a 2 in, minus, okay, 2 cubed is 8, times 8 is 64 thirds, minus 64 thirds, plus 2 to the fifth, I'm pretty sure is 32, isn't it? Yeah, I believe that's right. 2, 4, 8, 16, 32. Yeah, 32 fifths. Okay. The zeros, that's the advantage of doubling. Okay, real easy to do. All right, so this is a rho times. Now we need to get everything over 15. 15 times 32 is 160, maybe? Over 15 minus 5 times 64 is 320 over 15, I hope, plus, doesn't seem right. Is that right? Way big. Okay, let's go on. 3 times 32 is 96 over 15. Okay, there'll be a bracket here, but you can't see it. Okay, so this is rho times, add 90, this isn't coming out right at all, is it? Where have I botched up here? Or have I botched up? Seems to have done everything right. Let me do my 64 times 5. That seems right. Let me get my calculator and see if that will help any. The old gray cells aren't working well this morning. Okay. Okay. I was advising students this morning, so the advising's all over on my calculator here. Okay, on my phone. Okay. Let's do the 32 times 15. Oh, that's where I messed up. I think I did 32 times 5. Oh my word. And nobody caught me on that? What is wrong with you guys? Okay. 32 fifteenths is 15,360. Where in the world is my eraser here? There we go. I just did 5 times, not 15 times. Okay, but that number seems awfully big. Let me do that again. 32 times 15. No, that's 480. What's wrong with you people? So this is 480. Let me get my pen back. Okay. Minus 320, that would be 160 plus 96. 160 and 96 is 256. Anybody? 256 over 15. Okay, so that's our moment with respect to x. So the y bar, I'll try to come over here if I can get the pen to ever get down there. So the y bar is equal to that thing, 256 over 15 times rho divided by 32 over 3 times rho. Guess what? The rows go out, okay? And then you can do 3 will go into 15 5 times. And I bet you 32 will go into 256 8 times. Okay, so this would be 8/5. If I can get my pen to ever show up here, there it is equal to 8/5. That's the y bar. Okay, now picture our parabola there. Okay, 8/5 is 1 3/5, so it's just short of 2. So it's below halfway because the vertex, oh here it is, right here. What am I waving my arms about? So we knew the x bar was on the y-axis. It would be 1 3/5 would be right about there. Okay, and here it's done it again. I don't know why it does that. Okay, did it again. Right there, somewhere right in there. It's a little too low. That is our centroid, center of mass. Okay, and because the lamina is thicker at the bottom, that would mean it's below 2. It isn't halfway up there. So 1 3/5 actually looks a little on the be too close to the center, but that's what we get. Let's see what the book got. 8/5. Good for them. Okay, so let's go back and see how they did it. I know they did a few things differently. All right, so here they go. Find their center of mass. First thing to do, because center of mass lies on the axis of symmetry, you know the x bar is equal to 0, because everything's symmetric with respect to the y-axis. So the x bar has to be there. It took half of our work away. The mass we did just like they did, except they went -2 to 2. I did half of that, doubled it, and did 0 to 2. And we got the same answer, I think. Well, pretty close to it. Not the same integral. Well, the same integral, in fact. 4x minus x cubed over 3, but they just went from -2 to 2. You got the same answer, 32 rho thirds. 32 thirds rho, or however you want to say it. Now, to find the moment about the x-axis, place a representative rectangle in the region. They did. I tried to put it about where they did. And its y bar would be halfway up it, which would be f of x divided by 2. Okay? That's the y displacement of that one. and the rest of it is just the mass of it, which is the density, rho, times the area, which is y, times dx. Okay, so we just got a y bar over 2 times a y rho y dx. Okay, so get the rho over 2 outside, but then we're going to do the same trick we did before and double from 0 to 2, and that takes care of the dividing by 2. The book doesn't do that. They just did this, which is exactly what we got, and because the mass of the representative rectangle is the density times the function height times the delta x, that's exactly like we did when we calculated the mass. The m sub x is that rho from here, the 4 minus x squared over 2 from the midpoint of that rectangle, how far the center is from the x-axis, times, here's the rest of your density. Okay, this is your area, your height times your width. Okay, rho times the height times the width, that's your mass. Here is your displacement from the x-axis. So take the rho over 2 on the outside, double that and go from 0 to 2. They don't do, but anyway, they got the rho over 2 on the outside, and then they integrate. Well, they did it. No, the over 2 goes out here, so that would be 16 minus 8x squared plus x to the 4th. Integrate that, and you get rho over 2 times 16x minus 8 x cubed over 3 plus x5 over 5 from negative 2 to 2. Double it and do 0 to 2 is easier. And they don't do anything. They just show the answer 256 rho over 15. And the y bar would then be that answer divided by the answer we got of the mass on the previous page. This will go into that 5 times. Rows will completely go out. This goes into that 8 times, so you have 8 over 5, and that is your y bar. And there it is, right when the thing faded out. Now, this is now showing if you had taken a pencil point and put that lamina exactly there, right on x equals 0, y is equal to 8/5, that would be 1 3/5, you would balance that perfectly, even though it's not a regular shape. Now, of course, that means it has to be a uniform density, uniform thickness, all like that. Okay, why they show that, I'm not sure, but it's a neat picture. Okay. Now, the center of mass of a lamina of uniform density depends only on the shape of the lamina, not on its density. We just saw the density canceled out. So for that reason, the point x bar, y bar is sometimes called the center of mass of a region in a plane, or the other name for it is the centroid of the region, the center point of that region. In other words, to find the centroid of a region of a plane, you simply assume, I'll have to wait till this fades out a little bit. Fade out here. Get out of there. It's taking its sweet time to fade. There it goes. Assume that the region has a constant density. Call it 1. Who cares what it is? And compute the corresponding center of mass with rho equal 1. Okay? You know they're going to cancel out anyway. Okay. Now, they're skipping example 5s and 6. Do y'all want to see these, or do you want me to move on? Let me know. Some sort of response. You want to see them, or move on? Since I don't hear anything, I'm going to assume you want to see them. Okay, so let's do example 5. This is not theorem of Pappus. We'll go here and have to do everything on the whiteboard. Okay, let's clear the screen first. Okay. Find the centroid of the region bounded by the graphs of f of x is equal to 4 minus x squared. That sounds sort of familiar, doesn't it? I wasn't about to leave all that scratch up here. And the line g of x is equal to x plus 2. Okay. Now, sometimes it helps to have the picture. In doing the calculation, it really doesn't matter. But I want you to see the picture anyway, and you tell me how I'm doing on the thing. Can you see that graphic there? Yes, no. Move forward, backward, up, down, left, right. Let me know. Anybody? Okay, I can't tell. I'm tired of holding the book, so I hope you saw it. If not, look in the book, or I'm sorry if you don't have the book. Okay, now we really don't need it. We want the centroid of the region bounded by those two graphs. One thing we got to do is find the points of intersection, because that's going to be what we're going to determine our x's by. So let's set these two equal to each other. That's how we find what points they have in common. If they have them in common, they must be equal. So we have 4 minus x squared equal to x plus 2. Now, I don't know about you, but I prefer to have positives, my leading term positive. So I'm going to add an x squared to both sides. And subtract 4 from both sides. Now I'm going to reverse the sides, okay? So that would be an x squared plus x minus 2 is equal to 0, because this side is equal to 0. Can we factor that? I sure hope so. Okay, you know this has to be x times x. Because that sign is negative, this has to be a plus and a minus. We know the plus sign is going to win in the middle, so you better have plus 2 minus 1. Is that right? X squared minus x plus 2x is plus x minus 2, yes. So this is between x equal negative 2, which is where we were before, and x equal 1, which is not where we were before. And I'll tell you what, you're not going to be able to use the trick of symmetry, because it's not symmetric anymore. Okay, x plus 2 is a straight line with a slope to it, and the x squared, 4 minus x squared, is a parabola that's symmetric about the y-axis, but x plus 2 is not symmetric about the y-axis. F of x is an even function. G of x is a neither function. It's not even nor is it odd. Okay, it's a neither. So, first thing probably to do is get your mass. So what's the mass? And again, we're going to assume density is 1, so don't even mess with density. Okay, it's going to be the integral from negative 2 to 1. Now, the other thing we've got to figure out is who's on top here. Okay, well, we know the parabola does like that. We had that in the last one. The line here, x plus 2, does like this. So the parabola winds up on top everywhere. Okay, so that's going to be our f minus g, would then be 4 minus x squared minus x minus 2 dx. Okay? The height, the length of this, which is the difference between those two, times the width. That's it. And for some reason, it did away with my 1 up here. I hope I wrote it, but usually when that thing pops up, it erases something on the board. Okay. So let's clean that up just a little bit. That would be the integral from -2 to 1 of 2 minus x squared minus x dx. Now if you wanted to, and some people like to do this, put that in parentheses so you don't think only that last term has to do with the dx. Alright, so what would this be? That would be 2x, antiderivative of that is 2x, minus x cubed over 3 minus x squared over 2. Evaluate that from -2 to 1. I can do the 1. That's pretty easy. Okay? That's going to be 2 minus 1/3 minus 1/2. Okay. Now let's do the minus with the -2 in there. Well, the -2 plugged in here would be a -4, but you're subtracting it, so that's a +4. And then a minus times a minus is a plus, but then when you put a -2 in there, that gives you a -8/3. And then a minus times a minus is a plus, but when you put a -2 in here, that gives you a +4 over 2, so there's another +2. Alright, looks like we got 8 on the positive side. 4 plus 2 plus 2 is 8. 2 plus 4 plus 2 is 8. And on the negative side, we've got a -9/3, which would be a -3. And then you got a -1/2. So this would be 5 minus 1/2, which would be 4.5, which is 9/2. Now I'm hoping that's the mass. Let's see if it is before we get too far here. Yeah, that's what they got, 9/2. They don't do any of the hard work, they just write the answers down. So there we got the mass. Okay. And now we're completely out of room. Okay, so let's get our eraser and erase most of what we've got here, or at least part of what we got here. Okay, let's see what we can live with. Let's now figure m sub y. Okay, it's probably the easy part. So m sub y is going to be the same thing times, well, let's see. Moment with respect to the y-axis. We don't need this anymore, do we? We've already taken care of that. I should have erased that to begin with. Okay. I think I can get rid of this. And probably get rid of this, but I want to leave the 9/2, so don't let me get rid of that. Well, my eraser decided to quit erasing. I guess I went too fast for it. It's unusual for me, I'm not fast at anything. Okay, so let's get our drawer back in here and make this equal to the mass. Okay. Now, what I was just saying, the m sub y, remember, is exactly that same part here, but then you multiply it by its distance from the y-axis, which is x. And there it went and did that again. It just drives me nuts. Okay, so everything that we had before, we're going to multiply by x. And I don't know if you remember what those things were. It was a 2, so that's going to be a 2x minus x cubed minus x squared dx. Okay. Now, the antiderivative of that will be x squared minus, and this part is the same. Well, no, not quite the same. X fourth over 4 minus x cubed over 3. That's going from -2 to 1. Okay, again, I'll volunteer to do the 1. That's pretty easy. I'll come over here and do it. That's equal to 1 minus 1/4 minus 1/3. Minus a minus, okay? So minus -2 squared is +4. That's not looking good. Minus a minus is a plus. -2 to the 4th would be a 16/4 would be a +4. Ha! That's looking better. Minus a minus would be a plus times a minus 8/3. That's not looking good at all, is it? Oh, it's okay. Yeah, sorry. I was thinking it had to be positive. It doesn't have to be positive. The moment can be negative. Okay? It looks like it will be negative. Least common denominator is 12, so that would be 12/12 minus 3/12 minus 4/12 minus 32/12. Okay, and let's see what that comes out to be. A -39 plus 12 is a -27, I think. -27/12. They didn't do them individually. Shame on them. Okay. Well, let's see what happens if we put that over the mass, 9/2. That becomes a 6 there. That becomes a 2 over 3 here. This becomes a -9 there, so you wind up with minus 9/2 again. That can't be right, can it? It's -1/2. Okay, I messed up something somewhere here. Let's see. We got minus x over 4th minus x over, yeah, we got all those parts are right. It must just be in my calculation there. And I wouldn't be at all surprised if I didn't screw something up. Let's go back and do that last part. 927 3 times. We got 3 in the numerator and a 6 in the denominator. Yeah, that's a -1/2. Sorry about that. I was doing too much canceling out there. And this is -1/2. Okay, let's go back. Well, Okay. Trying to get too fancy with it. Minus 27/12 over a positive 9/2. And again, this will go into that 6 times. This will go into that 3 times. And you get a minus 1/2. Okay. Yeah, that's what they got. There's your x coordinate, is slightly to the left of the y-axis, negative 1/2. Now let's do the m sub y. That one's a m sub x. That's usually a little bit more involved. And the only difference here is, rather than x being the distance from the, that's the distance from the y-axis, now you want the distance from the x-axis. Well, the distance from the x-axis is 1/2 of the sum of those two. So you know the 1/2 is going to come out front, okay? And you have your integral from -2 to 1. Let me get some of this stuff out of the way, because it's going to be in the way. We know the answer is -1/2. This is your, yuck. Okay. I can't tell what it's doing here. This is your x bar. I don't know why it, sorry. Sorry, I didn't get the microphone out of the way in time to that split anybody's eardrum. Okay. Now, what we have here is now the sum of these two, and we haven't done that yet. When we add these two together, we get, yuck. For the life of me, I don't know what this is doing. The last thing I did, it undoes part of it. Okay. The sum of those two, f and g, will now be 6 f plus g is going to be 6 plus x minus x squared. Everybody agree? Add f and g together. 2 and 4 is 6 plus x minus x squared. That's going to be the extra term here. We did half of that by putting the 1/2 on the outside. So now we have 6 plus x minus x squared. That's the average displacement from the x-axis, okay? And then your mass was the same as before, this x minus x, no, 2 minus x squared minus x. Okay, back what we had before when you just did these together. 2 minus x squared minus x. And then you have your dx. All right. Now, what you have ahead of you here is a pain in the neck. It's multiplying a trinomial, 2 trinomials. Okay? It's doable. It's just easy to make mistakes. So let's try to be careful with it. 1/2 the integral from -2 to 1. Let's do the constants first. That's a 12. Okay. Now let's do the next term, minus 6x squared. But you know you got a minus 6x squared there. Here you have another minus x squared, so let's go and get that one done too. So that's minus 7x squared, but then here you have yet another x squared, or minus 6x squared. No, I already did that one, sorry. Yuck. This one is the one we haven't done. minus 2x squared. So you got 3x squared terms. Minus 6x squared minus 2x squared, that's minus 8x squared, minus 1 more is minus 9x squared. Okay, now let's do how about the x terms? Here's a minus 6x and a plus 2x. So I think that's a minus 4x. Now let's do the x cubed terms. This is a minus x cubed, and here we have a plus x cubed. Those add to 0. Thank you very much. And then we have a plus x to the 4th. Okay, I think I've accounted for everything, haven't I? We have the constant, the linear, the quadratic, the cubics added to 0, and this one. And then that's going to be my dx. Before I go through the mess of doing that, let's make sure that's what they got. X to the 4th minus 9x squared minus 4x plus 12. Good for them. Okay. Whew. All right, let's integrate it. Remember, your 1/2 is out front times, and this will be 12x minus 3x cubed. Catch that? Minus 2x squared plus x to the 5th over 5. Knew we're going to have a fraction in there somewhere, and this is going from minus 2 to 1. Okay. Now, I'm running out of room desperately here. Don't forget your 1/2 is there. Now let's plug in the 1 first. I can do that one. 12 minus 3 minus 2 plus 1/5. Had to be an oddball there. Then the minus 2 done in, which minus a 12 times negative 2, but that would be a negative 24, but it's minus, so that's a plus 24. Seems pretty big, doesn't it? Okay. Then we have a minus times a minus is a plus, but when you put a minus 2 in here, you get a 3 times 8 is 24. That's strange. A minus 24. Now if I did that right, those cancel out. Okay, no guarantee. Let's try it. Okay, minus a minus is a plus. 2 times 4 is 8, so it's a plus 8 here. And then finally a minus, but you got a minus here, 32/5. So I think that's a plus 32/5. Now, all sorts of places here for me to make an error, and I bet you I have, but let's do it our best shot here. So that would be a 1/2 times, let's add 12 and 8 is 20, minus 5 is 15. I think that's all our whole number parts, and you got a plus 33/5. All right, now how many fifths? Yeah, I hate this. Okay, I think that's just an ugly drawing. Oh no, that's the -2 from here. Okay, sorry. Okay, to get this over 5, 5 times 15 I think is 75, so you have 1/2 of 75 fifths plus 33 fifths. Okay, 75 and 33 is 108, I think. Half of 108 would be 54, so we got 54 fifths. Divide that by our 9/2. Hey, 9 will go into 54 6 times, so it looks like this is going to be 6/10 or 3/5. Yuck! Quit doing that. That doesn't seem right, is it? 12/5. No, I've botched something up somewhere. Oh no, 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 no. 12/5. When you invert and multiply, that becomes 6 times 2 is 12. Sorry, I did right at the very end. Had to make a really dumb algebra mistake. That's 12/5. That is right. So that would be 2 2/5. Okay. If you look at the graph, your x was -1/2, your y bar was 2 2/5, and that puts your, actually they put their representative rectangle, the dot in the middle, is not too far off from where the centroid is. It's not exact, but it's awfully close. -1/2 is the x-coordinate. That looks pretty close to that, and that's a little bit above 2 2/5. That's more like 2 3/5, but still it's not too far off. They didn't draw it in, but that's what you get. Your centroid is -1/2, 12/5. Oh boy. Any questions on that before I clear it? Okay. Then let's clear it out of the way. And now let's do, they have a statement here. For simple plane regions, you may be able to find centroids without resorting to integration. So that's what they're going to do here. I wish they had drawn it for me, okay? But they didn't. So I'm going to try to draw this with my tool here, straight line tool. Okay, I'm going to do the vertical axis here. I'm going to try to make it as vertical as possible. Okay, it's not, but let's pretend it is. Okay, and then we'll do our horizontal axis here. I'll try to make that as horizontal as possible. That's not very horizontal. Okay, now this is going to be divided into 6, so let me get my draw tool. Okay, and make that 3 here, and maybe 1 and 2 here, 6 out here, and 4 and 5 there, just as a rough guess. And then we want it 3 high. So let's make, come on, where are you? There you are. Make that 3, 1, 2, something like that. It's nowhere close to real. Okay. Now this first block here, I'm going to go back to my draw tool. Okay. And make that to right about there, and to right about, why did it do that? Let's just guess that. Okay. And then my next line, stupid thing that we have here, will be 1 to 4. 2, 3, 4 right here. Come on. This thing is so aggravating. Okay, let's just imagine that's close to, ooh, that's awful. Okay. To there. And the last one is a 2 by 2. So let's do from here down to there. Here to there. There to there. Okay. So if you can follow this, this is a, come on, where are you? Okay, this is a 1 by 3 box here. This is a 1 by 3 box here. And this is a 2 by 2 box over here. Okay. Now, what they say, you can locate the centroids, and here's one way to do it. Okay, I don't know if you've ever done this before, but let's try this. Yuck. This is such a pain in the neck. Do your diagonals like this. What in the world are you doing here? Okay. 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 I have a draw, and it starts off being a draw, and then it changes to be that. I can't do it. Okay. I guess you can't get real close to the edge. I guess that's the deal. Don't know why, but you can't. Or at least of the last one you did. Okay. This has rules that I don't know what the rules are. Did it again. Okay. And I can't draw the other one. Okay. So it's not going to let me. Okay. But you get the general idea. Here's the centroid of this one. Yuck! Here's the centroid of this one right there. Okay. And this is at 1/2, 3/2. Here's the centroid of this one. This one's at, now this is 1, 2, 2.5, that's 5/2, comma 1/2. And here's the centroid of this one at 5, 1. I couldn't draw the other diagonals, but you can imagine where they were at 5, 1. Okay? And that's what you see they got in the book. Okay? It's just simple geometry. The centroid of a rectangle is at the cross section of its two diagonals. Okay? That's what they said. Now, where do you go from here? Okay? What you now do is find the centroid of the entire region. Okay? Now you need the area of the whole region. Now remember, before we were saying mass, but remember we're assuming the density is 1, so basically the area of the whole region. The area of this rectangle here, if I've still got my pen, I must not. It says I do. Oh, it's because I'm not holding this thing right. Okay, the area of this is a 1 by 3, so this is an area of 3. This is an area of 3, and this is an area of 4. Okay? Now, we treat it as if all the area were at that centroid, and this centroid, and this centroid. So basically, your X bar then is going to be, this is 1/2 plus 5/2 plus 5. That would be 6/2, which is 3, plus 5 is 8. Over the sum of those. That doesn't seem right. Let's see, and the sum of those is 10. No, I'm sorry, I forgot to multiply the volumes, the area in. Sorry about that. Let me. Okay. All right, let's take it a little more slowly. It's 3 times 1/2, that is 3/2. Come on, here we go. 3/2 plus 3 times 5/2 is 15/2 plus 4 times 5 is 20 divided by the total area of 10. Okay, let's see if we can add those together. 3/2 and 15/2 is 18/2. That's 9 plus 20 is 29 tenths. And that's yuck. And that's equal to 2.9. 2.91, 2.9 is right about there. That doesn't look too reasonable for the X. Let's do the Y bar. 3 times 3/2, that would be 9/2, plus 3 times 1/2 is 3/2, plus 4 times 1 is 4, okay, all over 10. This is 12/2, which is 6 plus 4 is 10. That's going to be 1. Okay, well, that's right here. Didn't I have, yeah, no, 2.9 was here. So right about there. That's going to be where I think the centroid is. And what do they have? 2.91. Perfect. Okay. Now, it's not the average of the others. It's barely even in the area. The centroid on an irregularly shaped thing like this doesn't have to be in the area. Just imagine your shape was a donut with a hole in the middle. And if it's a uniformly spaced donut, that hole is where the centroid would be. The donut isn't even there. That's the hole in the middle of the donut. Okay, so yeah, it's okay for the centroid to be on a boundary like here because you have height over here, height over there. Yeah, there's your centroid. All right, finally, let's move on to the theorem of Pappus. Any questions on that before I leave it? Okay, let's go back to current slide. And, okay, theorem of Pappus. If R is a region in a plane, okay, some region in a plane, and L is a line in that same plane that R is in, okay, region of a plane, L is a line in that same plane, such that L does not intersect the interior of R, okay? So basically, here is your region R, right here. This, imagine the blue here, okay. Their picture leaves a whole lot to be desired here. I'm not really sure what the blue is. That's part of it, but it's not all of it. This is the region R they're talking about, I'm pretty sure. Just this reddish kind of region here. They show the whole plane there, but just this portion here is what they're talking about, the region R. Now L would be in that same plane, but not in this part of the plane. That's what they're trying to say. But L is in that plane, the blue plane, okay? But we're dealing with only the red rectangular part of that plane, okay? L's not in that rectangle. It's in the same plane of that rectangle, but it's not in the rectangle, okay? So if little r is a distance between the centroid of the R, here's the center of that rectangle, which is where the two diagonals connect. So there's that centroid right there. If R is a distance from that line to that centroid, R, okay, then the volume of the solid of revolution is simply going to be the circumference made by that centroid. 2 pi r, that's the circumference that the centroid made, times the area of this thing. So basically, you take your circle that is made by moving that centroid around and then multiply it by the area of r, and that gives it the volume of this thing. Area is length times length, the height here times the width here, okay, times a length, which is the circumference of that centroid as it makes its way around. There's your third length, and that gives you a volume, where A is the area of the region R. Note that 2 pi r is the distance traveled by the centroid as the region is revolved around the line. So that gives you the entire volume. Okay. Now, the theorem of Pappus can be used to find the volume of a torus. That's not a car, okay, different spelling. As shown in the next example, a torus is a donut-shaped solid formed by revolving a circular region about a line that lies in the same plane of the circle but does not intersect the circle. Okay, so here's what we mean. I like donuts, okay. Here's the circle you start with. Okay, that circle there, and here's the line. It's in the same plane of that circle, but not, it doesn't intersect the circle, okay? Now, centroid of a circle, of course, is the center of that circle. It's a lamina, a uniform plate, that would be the center, would be the centroid. That's 2 units from the, and here's, okay, find the volume of the torus shown here, which was formed by revolving the circular region bounded by x minus 2 squared plus y squared is equal to 1. Well, x minus 2 would be, if that was x squared, that would be the origin, okay? But x minus 2 scoots you 2 units to the right, plus y squared, that means y, you're only going up 1, so you got a circle of radius 1, but centered at 2, 0. And that's exactly where it's centered there. Okay? So find the volume of the torus shown here, which is formed by revolving that circular region around there. Okay. First, the area of this circle, that's the circle of radius 1. that would be pi times 1 squared is 1, so that's pi. So pi is the area of that circle, radius 1. Now, you take that centroid, which has a radius of 2, different radius here, radius of 2, 2 times pi times r, 2 times pi times 2, that would be 4 pi. So 4 pi times pi is 4 pi squared. That should be your volume of that centroid. Okay, says here you can see the centroid of circular region is 2, 0. So the distance between the centroid and axis of revolution is 2. Because the total area of the circular region is pi is equal to a, the volume of the torus is 2 pi r a, but a is pi, so it's 2 pi squared, or they take a long time, 4 pi squared, which is exactly what we got. All right, any questions on that? So that was example 7. And that finishes, no it doesn't. Oh, 4 pi squared is something on the order of 39.5. I always count pi squared as being awfully close to 10. 10 times 4 would be 40. This is half a unit off from there, so not a bad guess. 39.5. All right. 7.6 exercises. That took long enough to finish. Do either 5 or 7. They're both at Calc Chat. 7's at Calc View. Number 9's at Calc Chat. Number 11 or 13, both at Calc Chat. 11's at Calc View. Any of the odds, 15 to 27, they're all at Calc Chat. 15's at Calc View. 29's at Calc Chat. Either 31 or 33, they're both at Calc Chat. 33's at Calc View. 35's at Calc Chat. Either 37 or 39, they're both at Calc Chat. 37's at Calc View. Either 41 or 43, they're both at Calc Chat. You can explore doing those anyway. All right. 45, any of the odds 45 to 49, they're all at Calc Chat. 51, it should be at Calc Chat. 53 is modeling data. You can try it if you'd like. They say you might need some type of a, I don't know what they call it, graphing utility or something like that to help you do that. So I'll let you determine whether you want to do that. And then 55 is the second theorem of Pappus, which they don't give in the text, but they give here. And I'll let you decide whether you want to do that, and or 57, both at Calc Chat. So let's move on. Are there any questions on 7.6 before we move on to 7.7? Okay. 7.7 is this slide set, I think. Probably should have shut the other one down, but I didn't. Let me go back. Let me click here and shut that one down. Okay, let's discard that one. Now, okay, fine. Now let's go back to screen share and do 7.7. This time it should, yeah, there it comes. And we'll go from current slide. And we will also scoot this out of the way. All right, chapter 7, last section in it, application of integration. Now we're going to apply, I can't move it until I click on the slide for some reason. Fluid pressures and fluid forces. Okay, only one objective, find the fluid pressure and the fluid force. That makes sense. Now let's talk about some definitions here. Pressure is defined as the force per unit area over the surface of a body. Let's just give you an example of that. We're under 1 atmosphere of pressure. Believe it or not, our atmosphere, made up of air, does have weight to it. Okay? 1 atmosphere of pressure is right around 14.7 pounds per square inch. Pound is a measure of force, square inch is a measure of area. Now a square inch is about like your two thumb joints put together. Your thumb joints about an inch this way, two of them together make just about a square inch. Now think about how many square inches cover your body. It's a bunch, okay? Multiply that bunch by 15. I'm just rounding, 14.7, 15. That's how much weight our atmosphere is pressing down on your body. Whoa! That's a lot. It's a whole lot. Okay? But guess what? Your body is pushing back with actually more force than that. The reason I know that, if you were to cut your skin, don't, but if you were to, you bleed out rather than sucking air in. Okay? Obviously the force inside of you is greater than the force on the outside. Now, if you were to go somewhere like Jupiter, which you can't because it's a gas giant, but if you were with a much bigger atmosphere above it, you would be crushed, admittedly. Okay, so anyway, in general, the pressure is proportional to the depth of an object in the fluid. Okay, so here's a definition of fluid pressure. The pressure P on an object at a depth H in a liquid is P is equal to W times H. What is W? W is the weight density of the liquid per unit volume. That's what density, weight density means, weight per unit volume. Okay? And that's kind of a weird way to say it, the weight density of the liquid per unit volume. It's the weight of the liquid per unit volume, which is the density, the weight density. Okay? In some books, they will call that rho, like we were doing last time, rho sub W for weight density. There's also such a thing as mass density. We're not going to deal with that right now. So that's what pressure is at a depth H is the weight density, weight per unit volume, times the depth that you are. If you think of that, weight per unit volume multiplied by a dimension, a length dimension, that would give you weight per unit area, which is exactly what force per unit area, that's a pressure. So there's your first definition. Pressure is the weight density of the liquid times the depth in that liquid. Here are some common weight densities of fluids in pounds per cubic feet, which is pretty interesting because most things go SI units. This is doing US customary. Ethyl alcohol, 49.4 pounds per cubic foot. Now, a cubic foot's a pretty big volume, so that would be 49 pounds. Gasoline, less than that, 41 to 43 pounds, depending on the grade of gasoline, I guess. Glycerin, way denser than that. That's 78.9.6 pounds per cubic foot. Kerosene, denser to even than alcohol, 51.7. Mercury, oh my goodness, that's off the scale, for 849 pounds per cubic foot. Okay, that is a lot. 1 cubic foot of mercury, way more than you'll ever lift by yourself. Seawater is about 64 pounds per cubic feet, denser than alcohol, gasoline, kerosene, not than glycerin, and certainly not than mercury. Okay, pure water, fresh water, about 62.4 pounds per cubic foot. Okay, just to give you an idea of some of those weight densities. When calculating a fluid density, I didn't notice what the time was. Okay, we've got about 45 minutes left, right? Yeah, something like that. When calculating fluid density, you can use an important physical law called Pascal's principle, named after a French mathematician, Blaise Pascal. By the way, there's a couple more paper topics if you were missing one. Okay, Pascal's principle states that the pressure exerted on a fluid at some depth H is transmitted equally in all directions. Okay, exactly what does that mean? Not too sure, but we'll get there. For example, in this figure here, the pressure at the indicated depth is the same for all three objects. Here the object, the average depth is right there. It's tilted up like that. Now same size object, it's here but it's flat. Here it's vertical. But that's right at the middle of it. The average pressure, the pressure at the indicated depth, is the same for all three. Okay? No matter what the orientation of the object is. Okay. Because fluid pressure is given in terms of force per unit area, pressure is force per unit area, the fluid force on a submerged object, submerged horizontal surface of area A would then just be simply its pressure at that depth times the area. That would give you the fluid force if it's horizontal. Okay. Now here's example 1. Find the fluid force on a rectangular metal sheet measuring 3 feet by 4 feet that is submerged 6 feet in water, is shown here. Okay. Now, you got to pull several things into effect here. If you recall, your excuse me, I'm going to have to get a sip of something. My throat is incredibly dry. Sorry about that. Okay, let's go back to the things we just talked about. So a quick flyback. Oops, too much. First, pressure is density, weight density times depth. Okay, that's pressure. And fluid force is pressure times the area. Okay, so we know what pressure is, weight density times depth, and when we know what the force is, the pressure times the area. So find the fluid force, that's force, on a rectangular metal sheet measuring 3 feet by 4 feet, submerged 6 feet in the water. Okay, now I don't know, this is scary. I don't know what I've done with my style. Oh, there it is. Okay. These are expensive. I don't want to drop it. Okay. Oh, that's right. I can't write on I can, as long as I don't make any mistakes. And that's really scary to try to do that. Okay. There it is. Okay. What did we just say? Pressure is equal to weight density times depth, and force is equal to pressure times area. Those are the two formulas we're dealing with. So find the fluid force on the rectangular sheet of metal measuring, this was it, submerged in 6 feet of water. Now we're assuming there when they say water, we mean fresh water, and the density, which is the weight density W, I'm not used to calling it that, of water is, this weight density of water, okay, is 62.4 pounds per cubic foot. Okay, so we know the pressure is then 62.4 pounds per cubic foot times 6 feet, because it's 6 feet down. Okay, one of these feet wipes out one of those, leaving you feet squared. So that gives you your pressure of, and what do I do with my calculator or my telephone? Okay, here it is. 62.4 times 6 equal 374.4. I've just about lost my thing here. 374.4 pounds per square foot. Okay, now this is down here horizontal at the bottom, 12 square feet, so your fluid force would be 374.4 pounds per square foot multiplied by 12 square feet. Square feet go out, okay, and that would equal, yuck, almost lost it. Oh, I did lose it. 374.4 times 12 equal 4492.8. Okay, 4492.8, and that would be pounds. That would be the fluid force on that. Let's see how they did. 4,492.8 pounds. Now, if you are a physicist, the significant digits are driving you nuts, okay? Because here we have 3 significant digits on your density. You only have 1 on the 6 feet of water and the 3 by 4 foot plate, but let's just imagine those are exact measurements there. So you could put as many decimals after them as you wanted to, but you still can't get more than 3 digits here. So I would round this to 4,490 would be all you could get out of that. But this is a math book, not a physics book, so they don't worry with that. All right, so let's see how they did it. Because the weight density is 62.4 pounds per cubic foot. Okay. Goodness gracious. Okay. And the sheet is submerged 6 feet in water. The pressure on it is 62.4 times 6, which came out to be our 374.4 pounds per square foot. Because when you count pounds per cubic foot times feet, you get pounds per square foot. Then you take that and multiply it by the area, which is 12 square feet, and you get 4492.8 pounds. That sounds like a lot of force to me, okay, and it is. Now, here's another way of looking at that, okay. Just picture how much weight is on that. If you had a box there, like that red dotted line is, how much water is pressing down on that? Well, it's 4 feet by 3 feet by 6 feet. Well, that is 12 by 6, 72 cubic feet. Then multiply 72 cubic feet by 64.2. It's exactly what we did, but not in that order. 72 times 64.2, 62.4. If you multiplied right, 72 times 62.4. I said it backwards and typed it backwards. That's your 4492.8. That's how much weight of water is directly over that plate. That's the other way to look at what we just said, the fluid force on it. All right, enough said. Okay, this result is independent of the size of the body of water. The fluid force would be the same in a swimming pool or in a lake, okay? As long as you could have 6 feet down and 12 square feet area, it doesn't matter where you are, as long as it's fresh water. So here's the definition of force exerted by a fluid. The fluid force exerted by a fluid with a constant weight density, W, that's, it just sort of drives me crazy how they say that. The weight density is in pounds per cubic feet, okay? So I don't say why they say the constant weight density, which is pounds per cubic feet, per unit volume. Well, you've already said that, pounds per cubic feet. Okay, anyway. Against a submerged vertical plate, this time it's vertical. If you're going from C at the bottom to D at the top, or maybe it's vice versa, is, now what are we doing here? Here's your weight density of the water. Now it's the limit as your norm. Okay, did they not skip a lot here? I think they did. Let me make sure I didn't skip some. Nope. Okay. The limit of your norm, which is how you're going to split up this delta y here, because you're going down in depth, of the summation of your h of y, which is how deep you are at any y level, okay, times L of y. Now what in the world is L of y? That is the horizontal length of that region. Now they should have provided a figure here, and they kind of do in the book, but they should have done one here. So I'm going to hold this up for you to see. I don't know if you can see that figure there. Is that anywhere close? Now, with that figure in mind, if you've got your book, it's on page 506. Your plate is submerged, okay? All the plate's underwater. The top part of the plate is at D units beneath and the surface of the water is the plane with the x-axis in it. Your y-axis is perpendicular to that. That's how deep you are. So D, you're down at a negative y value, but not too negative, and you go all the way down to C, and that's the bottom of the plate, okay? Now, we're assuming we have a delta y strip that you're dealing with. That's the width of the strip, okay? The length of that strip is the length of the plate, okay? And that's your L of y. Now, remember, this plate doesn't have to be rectangular. They've drawn it as if it is, but what if this was curved? Then that length would be from this curve to that curve. Okay, so you got that. Okay. So this then would be, this is the depth at any y value, okay? This is the length at any y value times the delta y, okay? So if you think about this, this is a depth, there's a length, and there's a thickness. 3 length dimensions, that's a volume, weight per unit volume, times a volume, we give you weight, okay? So this is how you do it. You integrate that from C to D, okay? Of h of y, L of y. Now the h of y is yeah, they did show it over on the right. That's how deep you are at any value. Now, maybe everything comes out in the wash okay here, but it actually looks like to me, well, it just depends on how they're doing their calculations. I guess what they're saying, D is a slightly negative number, C is a much more negative number. So to go from C to D, that's a positive. Okay, so it's okay. All right, so there's your formula. I think they move straight into example 2. If you don't have your text, you can go to larsoncalculus.com for an interactive version of this type of problem. Okay, so here we have a vertical gate in a dam, has a shape of an isosceles trapezoid, 8 feet across at the top, 6 feet across at the bottom, with a height of 5 feet. Okay, as shown here. what is the fluid force on the gate when the top of the gate is 4 feet below the surface of the water. Okay, so here's what we've got here. We're going from, let's just identify ourselves. 4 feet, the top of the gate is 4 feet below, so that's your D. Okay, your C down here is another 5 feet down, so that's 9. So you're going to be integrating from 9 to 4. Okay, I'm sorry. -9 to -4. Okay, because everything's below. Okay, that's how they take care of their depths here. Okay, now your depth is the H that we were talking about, is the Y value. Okay, if your x-axis is the surface and your y-axis is the vertical here, okay, then your depth at any point here is y minus 4. Okay, that would be the depth here. The y here was 5 minus, right, I'm sorry, I said that backwards. The depth is just your minus y. Sorry about that. Okay, now this, it seems like to me they're messing up their signs like crazy here. The depth h of y is equal to minus y. That's just how deep you are. Yeah, so your depth here is your y. Okay, not anything else, the y. That's how deep you are. Okay, now you got to calculate what the length is here as a function of y. Okay, now this is there's a few ways of doing this. Okay, and I'm going to play around with a couple of them. I don't know, I hope this won't be more confusing than it's worth. We've only got 14 minutes left, so now what you do know, well, they don't start off, yeah, they're starting off with the length. Okay, what we're looking for here, and here we go. It's hard to find that little red dot. Okay, let's just imagine that that's supposed to be a straight line. Okay, this is the L we're talking about here, and we need to come up with L as a function of y. This is your y here. This is x-axis here. Here's the y-axis here. Okay, and these are all negative y's. Now, y is going from -9 to -4. Okay, remember that. Okay, now, basically what you need to do is set up sort of a ratio here. Your length here is 8 feet at a depth of, I'll put it -4 feet. Okay, and you also have a length here of 6 feet at a depth of -9 feet. Okay, and you're going to some value that's in between that. Okay, so basically you're going for every 2 feet you go down, okay, your length is decreasing by, no, I'm sorry, I said it backward. For every 5 feet you go down, your length is decreasing by 2. Okay, So you have a ratio of 2 to 5 or 5 to 2. Okay. So basically, kind of what I'm saying here is, to express this as another way, rather than, you kind of set up something. It's kind of like a equation for a line, kinda. Okay, y minus a minus 9, that's this thing, okay, is equal to this ratio I just talked about here. And let's see how they do it. 5. Okay, wait, now they're going to do something strange here, something I usually do. They didn't put their x-axis or y-axis there. They put their y-axis here. Okay, I can't draw straight. They put the y-axis on this line right here. Okay, and there in the middle. I can't get it to draw on the middle. There it is. There's the y-axis. So they're only going halfway. They're going to double this. Okay, and that's okay because the same force on this side as that side. So that's what they've done here. And because they've done it that way, you're going to be doubling everything. But that's why they say, and I was wondering where they got this, this y plus 9 that I have down there, y plus 9 is equal to, now notice the difference here is 4 to 3. So that's the ratio they're using. For every 5 feet you go down, you decrease this by 1. Okay? And then you do this times x minus 3. Now where did the x minus 3 come from? That's down here at the bottom. Okay? That is the thing. You're down here, y minus 9 at the bottom. So basically choosing this point right here. -9 down, this. Okay? And this line then, the length of this line, measured from the y-axis, that gives you, twice that gives you your L of y. So this then gives it to you, and you want to find the x in terms of y. So basically what this becomes is y plus 9 is equal to 5x minus 15, and that would give you, add 15 to both sides, and that gives you y plus 24 is equal to 5x, and then divide by 5, and you get x is equal to y plus 24 over 5. That's how they get their formula sort of in the middle of the page. I know we're running out of time, so I need to hurry with this. So the length is twice that. Okay, so your L of y is twice this. So L of y is 2x, because it's this side plus that side. So that'd be 2 times this. So this would be, one way to write it is 2/5 y plus 24. Okay. Yeah, and that's what they do. That's your L of y. Okay? Now, that's doubling that. You've taken care of the fact that your thing is there. Okay. Now, your y was your h of y was just y, or minus y actually. I don't know why they phrase it that way, but that's what they do. So now I think we have enough to actually do our formula where the force is the weight density, and we're assuming this is fresh water. So this is 62.4, that's pounds per cubic foot, okay, times the integral, and remember the integral is going from -9 to minus 4. Okay, because you're doing dy's out here. Okay, your depth is just minus y. Okay, and your height is this thing here. Well, I'm going to pull the 2/5 on the outside. So let's do the 2 out here and the 5 down here times this. We will worry about that later. And then just have the y plus 24 here. Okay. Well, let's multiply that through. This will be 124.8 over 5. That's a weird way to express it, but let's just leave. Sorry, this I can't get it right now because it's in the way. Okay, 0.5 times the integral from minus 9 to minus 4, and this will be, get out of there. How in the world do I get rid of that? Okay, here we go. Minus y squared minus 24 dy. Okay, see if we can do that integration down here. 124.8 divided by 5, and this will be minus y cubed over 3 minus 12 y squared. No, 24. Yeah, I thought there was a y there. I'm sorry. I can't erase here. 24y. This is getting to be a mess. Well, you evaluate that from minus 9 to minus 4, and we are running out of time. So let's just take their word for it here. They pulled the minus sign out front with the 124. That's sort of a good idea. I don't like messing with minus signs either. So pull that out front and then do the integration of this thing, and let's evaluate it at those places. Okay, so let me get my calculator set up here. Alright, now got the minus sign up front. We'll worry about that later. So here's y cubed over 3 evaluated at minus 4. So I'm just going to do 4 cubed is 64. Put a minus sign in front of it. So 64 divided by 3, and we'll make that a plus minus. That's equal to that. Minus which actually turns out to be a plus. Sorry about that. Okay, I think I did it right there. Plus no, I'm sorry. We have a plus there. So that is going to be a minus. 21 times 4. I'm getting lost on my things. Okay, I think that comes up to negative 105 and a third. And then we will do minus, which makes it, okay, that'll be a minus. Let me start over. Okay. No, it was right. 64 divided by 3. I'm going to wait and hold all the minuses till the end. Okay. Plus, and we'll make this a 21 times 4. Okay, 105, blah, blah, blah. Minus, okay, 9 cubed. I have one time known that, but I don't know. 9 times 9 times 9 divided by 3. minus that's a plus, sorry, plus, no, minus, I'm sorry, I had it right, 21 times 9. All right, get something on the order of 326.6667, you know, okay, and then multiply that by 124.8 divided by 5. I'll throw another minus sign in there. Yeah, I missed it. Okay. Don't have time to go back. I think we got the numbers right. I think I just punched them in wrong. So it gets to be a problem in calculations then. With all the minus signs and minus here, there, and everywhere, they come up with about 13,936 pounds would be what that averaged. Okay, now I think all the calculations are right. It's just that, boy, all those minus signs are enough to trip you up. Okay, we're out of time, so well, let's see, first thing, let's say we'll start on example 3 next time. We almost finished 7-7. So homework exercises here will be any of the either 3 or 5, they're both a Calc Chat, 3's a Calc View, 7's a Calc Chat, 9 through 13, they're all at Calc Chat, 13's a Calc View, 15 or 17, they're both at Calc Chat, 15's a Calc View, 19 or 21, they're both at Calc Chat, 23 should be at Calc Chat. You can explore doing 25 or 27 or think about doing them if you want to. You don't have to. They should be at Calc Chat. And then we can pick up the rest of those next time. You could try 29. I think you could do 29 or 31, possibly even 33. We'll hang out and do some of those next time. That will finish chapter 7. So what I'm going to do sometime today, after class is over with, I've got to come up with a test for chapter 7. I'm going to put it out there on Blackboard under whatever you call that, messages. I'll put it out there hopefully sometime today. If I don't get to it today, it may be tomorrow, but I'll put it out there before the weekend. Okay, knock on wood. Okay, try to have that and everything else in by Monday or no later than Wednesday if you can, and we'll be finishing that one problem in chapter wait, let me just take you through this. Sorry, I should have done this. Here's how they set it up, and this is the same thing we were doing. There's your depth of minus y. Okay, the length, they figured up this way, got the same thing we did. There is your x is that, and then multiply that by double that, okay, and then do your integration. There's the integration, just like I did. I brought the 2/5 out. I think they will ultimately. Yeah, there they do. They also bring the minus sign out, okay? And then they integrate this thing, and that's the same thing we got, y cubed over 3 plus 12. I did leave off my y. I thought there was a y in there. That was 12y squared. That's where I made my mistake. I thought it was there. I couldn't see it, so I changed it back to 24y. So that's where my mistake was. That's why I didn't get it. The thing, when you plug in those answers, you get a mess, a big mess, nothing but a mess, and that's where you came up with 13,900, about 14,000 pounds. Okay, next time we'll do example 3. If you can remind me, tell me there is no slide on this. We'll start with the slide set in chapter 8, so we won't have to do 7 anymore. Okay. I'll try to get the rest of it to you then this weekend. All right, good deal. Any questions? All right, I'm going to stop the sharing now, and if there's no further question, I'll end the meeting for all of us. So take care. We'll see you on Monday. Take care. See you tomorrow, Aaliyah. Okay. I did it again. We don't end at 12:15. We end at 12:25. Goodness gracious.